Good morning and welcome back. Today we will talk about chapter 14, second sections. What happened to here? It doesn't work. Oh, okay, good. It's very close to the end of this semester. We still have 4 classes left. Just four. Yes, just four. And 2 of them will be related to our final exam. Final exam, I will tell you how to conduct the final exam very soon. Very soon. Yes. And just cover 2 parts, 2 classes, 14.2 and 14.3. That's it. Okay. So don't worry too much. Last time we talked about radiation by velocity field. Here, let me show you. Radiation by velocity field. Radiation by velocity field. And we just skip the acceleration field. So velocity field, just constant motion. The idea of the velocity field actually will be related to special relativity. So we can use linear Wheeler potential to find everything, electric field, magnetic field, and use this relation. Or we can double check with special relativity, chapter 11. The result will be the same. Today, we will talk about uh, total power radiated by an accelerated charge. So we will consider acceleration field only, and we can skip this part. Okay? Here is an example. Not acceleration includes 2 parts. Acceleration and deceleration. That means the beta dot will be greater than 0 or less than 0. 2 possibilities. Here is an example. That's a very famous Brewster radiation. It's caused by deceleration fields. The field line and electric field generated by a negative charge. So you can see here, charge is negative, so electric field pointing to the charge. And at constant motion, constant speed, at first, constant speed, and then it stop quickly. Stop here. Stop. Stop quickly. So it generates some kind of radiation. This kind of technology has been used in many fields to generate high energy radiation, such as X-ray, gamma ray, and even the gamma ray. So accelerated field, including acceleration and deceleration, 2 parts. Okay, so we will focus on this part first and skip this part because we talked about this part before in previous sections. So today I will first generalize the famous Larmor formula, and I will give you 2 examples. After these 2 examples, I will give you just one problem. Okay, so Larmor's formula, we negate the velocity field. Just consider the velocity is very small. Velocity is very small, so beta is close to 0. So electric field can be simplified to ECR because beta is very small, so you can skip this part, very small. Just R here in a denominator, and N cross beta dot. Okay, a simplified version. N is from if you don't remember, let's go back. What is N? N is emitted from the point T prime to observer. That's N. And beta is from here to the particle's motion, the particle velocity divided by speed of light. Okay, that's beta. So N cross beta dot equals beta is here. Beta dot may be parallel or perpendicular to beta. Let's assume their angle is theta. Their angle is theta. Okay, maybe go back to this one. Let's beta here. Beta dot may be parallel or perpendicular. The result will be different, will be completely different. So I will show you, to give you two examples. Okay, so N cross beta dot and pointing, we can calculate pointing vector. S is the pointing vector in Gaussian unit. Gaussian unit, E is here, B is here. So eventually we got C over 4 pi E squared times N T prime. So the direction will be in the direction of N. Okay, reasonable. And substituting everything into here, this one into here. So eventually pointing vector in the N direction will be equals to this one. So we can calculate the power per studied angle, denoted as this form. Power radiated per unit studied angle. Okay? Is equals to E squared divided by 4 pi C. And this one will times 4 pi R squared. Okay? So eventually total angle will be times 4 pi R squared. Study angle will be 4 pi, and we can times R squared. So we can calculate this one. That's power radiated per unit study angle. Okay, that's this one. Just equals to E squared over this one times R squared. R squared and R squared cancel. So eventually we got this one. And this triple product can be simplified into this one. This is a simple operation. So from here to here, no big deal. And N is the direction of propagation. N is here, beta is here. N cross beta just equals to acceleration divided by speed c times sine theta. Times theta, capital theta, is the angle between N and beta dot, not beta. Keep this in mind, not beta, but beta dot. Okay. So if beta is in this direction and beta in this direction will be completely different. So E squared over 4 pi C cube. Why? Because of C squared. Okay. V dot square sine theta square. You can imagine the largest is the angle is pi over 2. That is the largest. Okay. Total power just integral total study angle. Study angle sine square 2 pi sine square. So eventually we got this one. And V dot in the non-relativistic model is dp over dt divided by m. Okay, that's V dot. Acceleration dp over dt divided by m. That's classical non-relativistic equations. Okay, so note that the quantity dp over dt, all the quantity in section 14.1 and 14.4 are real. So since quantity are real, we can write into this form. Jackson denoted as this one. Denote this one by this one. Okay, that's Jackson's notation. That's Larmor's formula, non-relativistic. The problem is, can we generalize a non-relativistic equation to relativistic equations? If we can do that, what will the relativistic generalization looks like? Remember, in 3 dimensions, a non-relativistic, we have momentum. But now we have 4 momentum. Can we generalize the momentum to 4 momentum? Yes, we can do that. Let me show you how to achieve this goal. The expression in 14.23 is here. 14.23 is here. Can be generalized to a relativistic form in which P will be a Lorentz invariant. Surprise! Total radiated power will be independent of Lorentz frame, independent of inertial frame, and is applicable to all electron energy. The procedure is as follows. Procedure is as follows. 做法如下. First, let's generalize P, smaller case p to capital P. And capital P comprises of 2 parts, E over C and P. That's 4 vectors. dP over dt, we just change to the capital P over d tau. So P will be 4 momentum. 4 momentum squared d tau. Therefore, this one from these equations, and these equations, P dP dot dP, d tau will be Lorentz invariant, and that's d tau is its own time, proper time, so will be independent of the coordinate, independent of the reference frame, inertial frame, and P dot P is a constant, is an invariant. Once again, in terms of P and E, we just write it down. It looks like this one. Wow, the proportional constant is the same. dP absolute value square 1 over C square because of this one. Okay, you can check chapter 11 and see you can find this one. Okay, we can convert. Tau is the proper time, and normally we prefer lap time. Lap time and the proper time is dt over gamma. Okay, time dilation. So gamma is greater or equals to 1. So gamma times d tau. Lap time will be greater. So P equals to this one. Oh, we recognize this one. We recognize this one. So for the non-relativistic effect, gamma will be very close to 1. And change in energy is small. If the change in energy is small, this equation just looks like this one. Okay? So equation 10 agree with the result derived from 14.14 next section. Okay, so we got this one. This one looks This one is a relativistic generalization of Larmor's formula. P equals to this one, and intent can be put in different form. People may not like this one because this one looks okay, but difficult to calculate. So we can change gamma. We know gamma is shown here. Gamma square is here. Okay? No big deal. Just write it down. So gamma square equals to 1 minus p square. We have gamma, we have p. We can rewrite these equations. Gamma p 1 minus p square over gamma square m square c square. P square, we replace v square with p square over gamma square m square. Okay, just a replacement. And then gamma square can be write into this form. Okay, not surprise. Just gamma square and 1 over this one. We just rewrite these equations. Gamma square equals to 1 plus p square over m square c square. It's a simple operation. I don't want to consider it as an extra bonus because it's quite simple. You can derive this equation easily. So gamma square equals 1 plus p square over m square c square. So we can rewrite gamma into this form. Therefore, the e over dt mc squared d dt gamma. Okay? So we can change the change in gamma into the change in p. Okay? So by doing so, we got this one, proportional constant, the same. And this one gives us 1 over 2, 1 over 2. So we have 2 here. And this one becomes the denominator. And this one, 2p m squared c squared dp over dt. So 2 and 2 cancel. And we have 1 m here. And we have another. This is gamma. This is gamma. Okay? P over gamma m dp dt. Therefore, it's v dp dt. Substituting v dp dt for e, we got this one. This equation 11. Okay? Equation 11 just change the e over dt to this one. No big deal, but it changed a lot because we know p here is the absolute value, and p is a vector, but this one is the absolute value. dp dt expresses both direction and amplitude variations of p, but dp over dt only expresses the amplitude variation of p. That is absolute value of p. Okay, that's the major difference. So let's compare equation 10 and 11 again. 10 here, just change here, becomes v squared dp over dt squared. Okay? Okay, so we have two expressions. Equation 10, we write into this form. And equation 11, we write into another form. Now, let me show you. We can, in terms of beta, another expression. In terms of P and E, that's equation 10. In terms of P and gamma, gamma P and E, that's equation 10. Gamma P, that's equation 11. Now, let's change to gamma beta and beta dot. That's equation 14.26. Okay, so dp over dt is here, and p comprised of two parts. P comprise two parts. Okay, P is equals to gamma m beta times c. MC can move to the front. So gamma, beta, you can differentiate on gamma first and then differentiate on beta. So this one comprises of two parts. And this one differentiate on gamma. That's gamma MC square. We have another square here and c divided by c square. So eventually we have m square c square. So the proportional constant is the same. Okay, we can combine this one. So this one is beta square d gamma square dt d gamma dt square plus 2 beta dot gamma d gamma. Okay, plus gamma square beta dot square minus d gamma dt. Okay, okay, then we can simplify this one because the gamma dt beta square minus 1, so just equals to minus 1 over gamma square. Okay, so these two combine together. Yes, these two combines into here. But remember, the gamma dt equals the dt 1 minus beta dot beta square root. Okay, so after differentiate, it gives us 1 minus 1 over 2 and 1 minus beta dot beta 3 over 2 minus 2 beta dot cancel. Okay, so eventually we have gamma cubed minus minus, so it's plus beta dot. Okay, so this one, the gamma dt is replaced with gamma cubed beta dot. Okay, great. So we can simplify into a minus sign. And this one, the gamma dt, once again, substitute to here. So once again, we have beta dot times beta dot square. And last one here. And these two, what's the difference? Minus plus 2. So minus 1 plus 2 is just 1. Okay? Okay, so we can move these terms to here. And gamma to the fourth. And this is gamma square. So it's 1 over gamma square if we move gamma to the fourth to the front. 1 over gamma square just equals to minus 1 minus beta square. So eventually we can rewrite this one, the proportional constant here, beta square plus beta dot square minus beta dot square. Okay, it's not finished yet. We can, this one, beta square, can be rewrite into this form. Really? Yes, we can do that. How? We can use the first quadruple product. A cross B dot B C cross D. The result will be A dot C B dot D minus A dot D B dot C. So A cross B equals to, that's inner product, A cross B dot A cross B. So the result will be A square B square minus A cross B square, right? The same, A cross B square. So this one, can be rewrite into this form. Okay, much simpler, much simpler. Okay, because uh, uh, beta square, what should we have? What should we have? Beta dot square. We just write this one. This one will give us these two terms, but with a minus sign. Okay. This one give us these two terms with a minus sign. Okay. So eventually we got P equals 2E squared. What happened here? Oh, let's just here. We consider everything. 2E squared, 3C, gamma to the 6, beta dot square minus beta cross beta dot square. Okay, so now we have three expression. Equation 10 here in terms of gamma, P, and E. That's not convenient. Equation 11 in terms of gamma, P, and P vector, and P, absolute value. Equation 14.26, we have this one. Okay, we have three expression. Which one is more convenient? That depends. Okay, now I will give you two examples. Example 1 will be linear acceleration. Linear accelerator. That is, P is perpendicular, is parallel to the acceleration force. In terms of P, that's equation 11. So P equals to gamma squared dP squared over dt squared. Therefore, because it's linear acceleration, so in the same directions, just like a linear accelerator, the particle move in this direction and acceleration force is parallel to this one. Okay? So this one times minus this one. So eventually we have a simple relations. Proportional constant, the same. Gamma square, 1 minus beta square times dP over dt. Because of this one is 1. Just this one, substitute to here. And this one is the same as this one. 1 minus beta square, just cancel with gamma square. So therefore, is P total radiated power is 3E squared over 3m squared C cubed dE over dt squared. And we know dP is equals to force dt. dE is equals to force dx. That's the work by a small displacement. That's the momentum change by for a small time change. So dp dt equals de dx equals f, right? From these two simple relation, we got dp dt de dx. So we change here to here. That equals to the force. That equals to the force. So if we change dE dx, we just move one turns. dE dx, one turns, divided by P divided by dE dt. And this one just change to here. dE dt. One V dt is dx. Okay? And dE dt cancel with this one. Cancel. So eventually we have dP over energy change rate. Energy change rate. That is the energy we give it and the energy radiated. Okay. P is the radiated power, total radiated power. The EDT is external supplied power. How many energy we provide for this charge in a per unit time. Externally supplied power. Okay, so this one is 2e squared over mc squared, just shown here, divided by 3mc squared, dE dx. This one is very small. If we accelerate the particle, the radiated power is actually very small. Radiation losses are completely negligible in linear accelerators. That's good news. That means we can use the linear accelerator to accelerate the particle, and the particle lost energy just a very, very small amount. That means we can use linear accelerator to accelerate the particle, accelerate the particle, accelerate the particle. That's good. That's very important for linear accelerator. But how to extract the energy? This is accelerator. To extract the energy, we need circular accelerator, just like synchrotron radiations. Okay, let me show you equation 11 once again. And this time, it's a constant, a circular accelerator. So the P will be the P change rate here will be very small as we compare with this one. This one is the centrifugal force. Okay, so this one should be much greater. This one is circular motion, and P will be almost constant. We just change the directions. For a circular accelerator, this term is very small, and this one is centrifugal force, much larger. So we consider these terms only. And this term, and the direction is in the direction of theta or phi, doesn't matter. dP dt is P dt over E theta times the E theta dP dt. And this one is negligible. The E theta always changing with time, with the angular frequency, omega. And the angle will be in minus rho, because always change in minus rho directions, minus E rho directions. So that will centrifugal force, omega P E rho. So dP over dt, the absolute value will be omega P. Substitute this one into here. Eventually, we got 2e squared gamma squared, omega squared P squared divided by 3m squared C cubed. Okay? And omega equals to velocity divided by radius. Okay? Velocity divided by radius. That is, velocity equals omega times the radius rho. And P equals gamma mv. So eventually, P total radiated power equals to 2e squared times c squared times c divided by 3. M squared is cancelled with m squared, and gamma squared is used here. Gamma cubed. Oh, sorry, gamma to the fourth. Omega squared is replaced with v squared, and v squared divided by c squared. So we have beta squared here, and we have another beta squared. So eventually, the total radiated power is shown here. Note that 14.31 is an exact expression for P if the particle is in uniform circular motion, that is, if dp over dt is exactly 0. So that will be an exact radiation. This radiation is relatively large. So we can accelerate a particle and change its angle, change its direction will give us the radiations. So we can accelerate and decelerate up to our requirement. Okay, so let me rewrite this equation again. Rewrite this equation. If delta E is the radiation loss per revolution, per turn, from here to here, that equals 2 pi rho over V times P. 2 pi is circumference. V is the time. V is the speed. So that's time. Time times P. That's period times P. So eventually we got these relations. We got evidence. Delta E will be 4 pi. 4 pi. 2 pi is 4 pi over 3 E squared times rho. And another rho cancel with this one. So we have rho here. And beta to the cube. Why? Because we have V here. Simplify. And we have gamma to the fourth. And beta is very, very close to 1 because particles move very fast, just like synchrotron radiations. So beta very close to 1. So eventually, just put everything. It depends on gamma. 8.85 times 10 to the minus 2. E in terms of GeV. GeV divided by rho in meters. So the result will be MeV. So for early synchrotrons, earlier version, loss energy is small. However, now it's much, much larger. For synchrotron radiation, 1.3 GeV, the loss energy 72 keV per revolutions. Okay, so that means if you rebuff one turn, you lost this energy. If you rebuff 2 turns, you double, lost more energy. Therefore, you should give this energy. You should compensate the loss of the energy. We need accelerator. That is the Doris cavity. Go back. This one. This cavity is used to accelerate the charged particle. Just play a role just like linear accelerator. So this cavity, because electric field is the same as the particle motions. So it's a linear accelerator. Okay, good. The total power radiated in circular electron accelerator P in watts. MeV, delta E in MeV cross J in M. Okay, that's the total loss. It lost a lot of energy, so we need cavity to compensate the loss of the energy. Let me give you a problem. If a charged particle is in uniform circular motion, just like the previous case, is an exact expression for the total power it radiated. Uniform circular motion shows that the total power has the same value as viewed in the rest frame of the particle. go back to this one. That is this one. That is, if we see a particle that is at rest, the particle rest frame, the result will be the same as this one. Let's see. That means P will be a Lorentz invariant. Consider an instantaneous position of the charge located at the bottom of the orbit. Instantaneous of the charge located at the bottom of its orbit. When the charge moves horizontally to the right at velocity v0, the charged particle moves horizontally to the right at velocity v0. The acceleration A perpendicular. A perpendicular means the perpendicular to the motions. A is beta dot. C times beta dot points vertically upward with this one. V0 square over rho. Rho is the radius of circle. That's the circle. That's the radius. Built in the rest frame of the charged particle. Let's change frame. That's the left frame. And we change to the particle frame. Lower figure. We will see problem 11.5 in chapter 11. In this case, A perpendicular just move in these directions. Okay, so in the prime system, we will convert from, we use the transformation. A parallel will be 0, so no distance. A perpendicular will be this one. So we got this one. This one is 0, and perpendicular in the rest frame, particle frame, and the left frame is different. That's left frame we see from the laboratory, and that's particle frame we see from the particle viewpoints. It differs by gamma 0 square. And then the acceleration of the charge is vertically upward in both frames, and it's different by gamma square. Since the charge is at rest in the frame K prime, okay, Larmor's formula in 14.23 becomes exact. We can use Larmor's formula. So Larmor's formula is here. Because beta is very close to 0, it's exactly 0. Therefore, we just substitute everything into here. So eventually we got these terms. This terms is the same power as viewed in the left frame. Doing. This one, right? Equation 14.31. The result here, P equals P prime, is consistent with the fact the total radiated power is a Lorentz invariant. Total radiated power, P, is a Lorentz invariant. It's a proof, a simple proof. The total radiated power is a Lorentz invariant. However, the angular distribution of the radiation will be different in two frames, of course. And angular distribution of the radiation will be different in the two frames. We will show later in 14.44 that for the same acceleration, the angular distribution depends sensitively on particles' velocity. That's another story. So today I will stop here. We just cover 25. to 33, 9 pages. Okay, I will stop here. See you next time.